Topic in Module 3 is Characterization Techniques. Characterization is the process of identifying various particles by particle shape, size, surface properties, change properties, mechanical properties, and microstructure. There is a broad range of commercially available practical characterization technique that can be used to measure the particulate sample. The particulate or particle size and shape distribution. The shape of the powder is characterized by the dimensionality of the particle and its color surface, counter surface. An ideal system of shape characterization is given in the issue. That is, for the two-dimensional, it is having dendritic or electrolytic, and one-dimensional acicular chemical decomposition, and irregular shape, atomization, chemical decomposition, and angular shape for mechanical disintegration, carbonyl. Most powder particles are three-dimensional in nature, and they may be considered as being somewhat equiaxed. Spherical particles represent the simplest and ideal example of this shape. Porous particles differ from the irregular ones because of the presence of porosity, which itself may be the very irregular both in both shape and size. A large amount of porosity makes any shape characterization very difficult. In a real mass of powder, all prepared in the same manner, all the particles will not have the same exact size, even though the shape may be essential the same. Consequently, we must deal with size distribution when accurately describing powders. There are various methods one may be used to calculate average diameter. Particle size, therefore, is not coincidence quantity, but for any given nanospherical or non-spherical particles may have several values with a different meaning depending on the sizing method used. Particle size distribution curves relate to the particle size to the corresponding fraction of the powder with that size. In unimodal distribution, there is one high point and maximum amount of the certain critical size. Okay. The polymodal distribution consists of two or more narrow bands of particle size, each within a maximum with virtually or no particle between such bands. The broad band distribution simply corresponds to a uniform concentration of particle size over a rather broad size interval with virtually no particles having size outside this range. The irregular distribution represents a continuous and finite vibration of the particle sizes within a relatively broad range. It can be thus concluded that the particle size distribution is necessary to complete the characterizations. Now, the electron microscopy of powders. Powders are some of the hardest materials to mount. They agglomerate and hard to distribute evenly on a surface and can charge easily and fly off the amount in the vacuum and under the beam. You need to try get one layer only of powder onto the mount. If it is piled up, only the top will be coated, and when the sample shifts, the conductive surface will disrupt. It is also important to make sure that you get powder that is representative of the material. Since settling can occur, ideally a rifle splitter should be used for powders. But in practice, mixing the powders thoroughly with the spatula is usually enough. Carbon tape or paint makes a good adhesives, both for most of powders. Sprinkle the powder lightly with a spatula, press lightly to sit, and spray with canned air to remove loose materials from the top. If you are going to do particle sizing under the image analysis, is critical that particles do not touch. Oven has a jet depression devices that works well to disperse particles in a stream of air onto an adhesive surface. Another option for the fine powders is to disperse them in a polar liquid such as alcohol, but several drops on a glass slides and allow the alcohol to evaporate. Some of the supply catalogs have liquids designed to both disperse particles and act as an adhesive. Thank you.